Okay, I want to reiterate how important it is to get these moments correct and the signs for the forces correct. So I'm gonna reiterate this and make sure we've got it and do some more examples. So remember, the moment is the force times the perpendicular distance between the line of action of the force about the point about where you're taking moments. So again, we have to figure out the line of action, and then we take the distance, the perpendicular distance from the point to the line of action. Okay, so you must establish the line of action of the force you're considering. Now, for this problem, it's extremely straightforward, and that distance is extremely straightforward, but I'm focusing on this so that we get it right when it's more complicated. So, like I say, we got to get the signs and the equations correct, because everybody gets force times distance, to be honest with you. So, you've got to understand. Everybody knows clockwise and counterclockwise, but we have to think about it and get it right. So you must focus on the point about which you're taking moments. So one way to do it is to, in writing the moment equation, just write all of the force times distance terms, and then go back and put in the correct signs. That's a way to do it, because everybody gets force times distance. Come back, excuse me, and get the signs. Okay, so now remember, so when we do this, we have to pick the center of our clock. We're taking moments about point B, for instance. That is going to be the center of our clock. So, so moments about point B, the center of the clock is at point B. And the hand of the clock should go from point B to the line of action of the force. Okay? And it should be perpendicular to that line of force. So in other words, here's our beam problem. This is the same one we did. And here's point B. Here's my line of action of my force for my 10 kips. Well, how does that look on a clock? Well, it looks like this. There's our clock. There's our point B. There's our hand. So there's our clock hand. It goes like that. And then we have our 10 kip force. And what does it make it with the hand do? It makes it go counterclockwise. It's counterclockwise, so it gets a negative. It gets 10 times 15, but we put the negative sign out front because it's counterclockwise. When we do, now we're going to take AY as our force. We're still taking moments about point B, so B is still the center of the clock. Here's our line of action of our force. The distance here is 10 feet. And so here's our clock. Our clock still has B as the center of the clock. Here's our hand of our clock. It's there. But now my force A is going upward, which causes that hand to go in this direction, which is clockwise, which means it's positive. So it's AY times 10, but it has a positive sign because it's going clockwise. And we're taking clockwise being positive. So now what do we do with the 20 kip load? Well, we've got BY again. There's our force going down. So here's our clock. Point B is at the center of the clock. There's the hand. There's the 20 kip. It goes counterclockwise. So it's going to be negative. So it's going to be 20 times 4, but negative. So negative 20 times 4 when we look into our equation. Now, how about when we take moments about A? Well, when we take moments about A is going to be our center of the clock. So, for instance, when I look at force By, there's our line of action. The distance from point A to the line of action is 10 feet. So we have A, here's our clock. We have A at the center of the clock. There's our clock hand, and By is going upward, which causes a counterclockwise rotation. So it's By times 10, but negative because it's counterclockwise. And remember, we have to be true to our drawing. We started with this free body diagram, and we have to follow that free body diagram. We can't start changing things. Okay, so here's another example. And let's do this one. Now notice it's a beam, and I've got an 8-kip load here at the end of the beam. Well, you may have recognized that this is a diving board. This looks like a diving board. Okay, so obviously, very heavy load at the end of the diving board. But if you remember what a diving board looks like, we've got a roller here, and we have a hinge here. And, we know what this diving board is going to look like when it deforms. It's going to look like that. Somebody stands on the end and bounces up and down. You can, if you look closely at the shape of that diving board, it's going to look like that. So it's a diving board problem that we're going to look at various times. Okay, so what do? We have to first draw the free body diagram. And I come in, I draw my dash circle or dashed loop. Comes around like that. And again, I have to draw exactly what's in that dashed loop. So, for instance, I can use my copy and paste function. So just to show exactly what we have to draw, do that, I go copy, I go paste, and there it is. I've got that. Now I have to pay attention to where I made my cuts. I made a cut right there, which is where I wanted to make it. I made a cut right there where I wanted to make it. Where I've made those cuts, everything else is in the air, right? Everything else, all of this is in the air. That's air, air, air. I don't need to do anything. Air, air, air. I've only made an imaginary cut there, an imaginary cut there. And so I have to put a force or forces at those locations. That is a roller, which means I do just a vertical force. That is a hinge, which means I put both a vertical and a horizontal force. And I label them like that. So that is my free body diagram. And that free body diagram then is what I'm going to use. So this is what I have. It's my initial free body diagram. It has unknowns, letters next to the things we don't know. And now what do? Well, let's start with the easy one. I take the sum of the forces in the x direction equals 0, bx equals 0. So bx is the only force in the x direction. And again, I write a sign here. To the right is positive. So bx equals 0. Now I'm going to take moments about A. So this is the center of my clock, A. And, we can do force times distance. Well, 8 times 3. So I write down 8 times 3. By times 5. By times 5. And notice Bx goes through point A, so I don't even need to include it. But now I look at the signs. Well, what is the sign going to be? Well, I'm taking moments about point A. Here's my hand of my clock. That's sending that hand of the clock counterclockwise, so it's negative. for BY, there's the hand of my clock. There's the force. What does it do to that hand of the clock? It sends it around point A like that. It's also counterclockwise, so it's negative. So I have minus 8 times 3 minus BY times 5 equals 0, because everything equal to 0. I solve for BY, and I have to follow, good algebra. Tells me BY is negative 4.8. I take moments about B. So now B is the center of my clock. Now remember, I keep using the initial free body diagram. There's the center of my clock. For this, there's my hand. It sends the hand counterclockwise. So it's, it's 8 times 8. And I just went through it, so it's negative 8 times 8. For AY, here's my hand. There's the center of my clock still. That's clockwise. AY times 5. AY times 5 is clockwise, so it's positive. I solve that equation. I get AY is 12.8 kips. Now the next step, again, this is very important, is that you now take your initial free body diagram and you now substitute these numbers here that we found. So we got to be true to those numbers. And what does that mean? I got AY is 12.8. I cross that off. I write 12.8. BY is negative 4.8. I cross that off. I write negative 4.8. This one's 0, so we just eliminate it. Now, so that's the way. You have to follow this method precisely. Now, so we end up with this. 12.8, negative 4.8. Now, here's the way that we handle that. We don't like to see this negative sign here. So the way that we handle it is this. So it's... instead of going upward at a negative 4.8, that means the same thing as going downward at a positive 4.8. So the way that we handle that negative result that we came in with is that we then flip the arrow around, point it downward, right there. So this is our final free body diagram in here, and this is what you get graded on right there, drawing that correctly. So, and then we want to do our check. We do our check. I look at this and what do I see? I see going down, I see 8 and 4.8 is going down is 12.8. Going up is 12.8. It's equal. So that does not a guarantee, but it gives me confidence that I have the right answer. Again, if it's not equal, then you have to redo the problem. You got to rework it. Now, as we said, the diving board deformation, it looks like what? It looks like this. Somebody stands on the end of the diving board, and what do? If you look closely, you're going to see the deformation of a diving board goes over the roller and goes down. It goes, the diving board goes up in that area, in the region. It goes down in this region. So now, let's look at our final free body diagram. Our final free body diagram looks like this. And now what does it mean? It means, or how do we interpret that? What we learn is that these forces are what the supports put on the diving board. In other words, this support here is pulling down on the diving board. That's what that says. That's what we concluded. So it's pulling it downward. This support here on the roller is pushing upward. So what you need to learn is the reactions shown on the final free body diagram represent the forces that the supports apply to the beam. That's how we look at this. So We show the beam, and then the forces are applied to the beam. Now, for this diving board problem, we can see that the far right, the hinge, is pulling the diving board down. It's holding it down. This pulling downward is to prevent the diving board from flipping over and going into the water. In other words, if I don't hold the diving board down at this point, is what we're doing, what's going to happen to this diving board? It's going to, it's going to rotate about this point, and it's going to go like that and rotate and fall into the water. So what do we see? That this point holds the diving board down. And so what do I know? This point's got to be anchored into the ground. It's got to be anchored into the ground. Otherwise, this diving board will flip over, and if it's not anchored down, it's going to lift up. It's going to lift up, and it's going to fall into the water. So a real diving board must be anchored in the ground, because what is the diving? The other way to look at it is, what is the diving board doing to the anchor? So the diving board here, what is it doing? It is, I'll draw the anchor here. If I draw the anchor, what is the diving board doing? It's lifting up 4.8 kips. Okay, it's pulling that anchor upward. So in other words, we have to have an equal and opposite here. In other words, if this is pointing downward 4.8 kips, this must be pointing upward, equal and opposite. And must be going upward. So the diving board is pulling upward 4.8 kips. So you may have to make sure, if you're designing the diving board supports, you have to make sure that that anchor can pull upward 4.8 kips in this particular case. So that is the meaning. You need to know the meaning. You need to learn this. The reactions tell us what the supports do to the beam. Okay, so this is your first homework problem. I want you to follow this method and find the reactions for this beam. And in this beam, it's, I've got 12 kips there, I've got 8 kips there, and here are all the dimensions. And so what you should do is pause the video, and you need to draw an initial free body diagram, a final free body diagram. So pause the video here and do this problem. This is a really important step. Make sure you do the problem yourself. Okay, assuming you've done the problem, now here's the answer. So what do? We start out, we draw our free body diagram by making a closed loop. And where have we made, when we do that, where have we made cuts? We've made cuts at that support and that support. This is a hinge, this is a roller. And so for the hinge, I've got 2 forces, AX, AY. For the roller, I've got 1, BY. This is my initial free body diagram. So hopefully you got that initial free body diagram correct. Now what you're going to do is you're going to take moments about A and moments about B. So remember, that's the way I want you to do it. Moments about A, moments about B. So what do we have? Moments about A. I'm taking oops. So we have to look at our free body diagram. I put it in the wrong place there. So we don't do that. We go to our free body diagram to write our equations. That's very important. That's the whole purpose of the free body diagram. So I'm taking moments about A. Well, what do I have? I've got 8 times 3, 12 times 9, BY times 13. So one way to do it is just write those down. So I've got 8 times 3, 12 times 9, BY times 13. Then I think it through. Are they positive or negative? Well, I'm taking moments about this point. That's going to be counterclockwise, so it's negative. Again, moments about A. That's going to be clockwise, so it's positive. This one is going to be about A, counterclockwise, so it's negative. So I have all those. I've got the signs correct. Now I just use algebra to find my solution. It's 6.46 kips. Now I'm going to take moments about B. So now this is the center of my clock. I've got AY, whoops, let's just do the force times distance. So it's AY times 13. I've got 8 times 10. And I've got 12 times 4. 12 times 4. I'm taking moments about B, so this one goes clockwise, so it's positive. This one goes clockwise, so it's positive. This one goes counterclockwise, so it's negative. I solve just using algebra, negative 2.46. That negative sign is important. So now what do? Remember, I come in here and I just cross that off and I put 6.46. Some of the force in the x direction is 0, so this is 0. So this is good. So get rid of that. But now I cross that off, the AY, and I put in negative 2.46. So I end up with this, but I don't like this negative sign, so you have to eliminate the negative sign or I take points off. So you have to correct it. We don't want a negative sign in our final free body diagram, so what do? I take it and I flip the arrow. Instead of up, I put it down and I put a positive number there. So this is my final free body diagram. I check, does up equal down? And what's going down? I've got these two going down, I have these two going up, and they both add up to 14.46. So the answer is yes, you need to do that check. And yes. Okay, here's another one. Do this one. Again, pause the video. It speaks for itself. Find the reactions. Draw the initial free body diagram. Draw the final free body diagram. Okay, I'm assuming you've done that. Now I'm going to go through a little bit faster. Here is my free body diagram. Now in this particular case, I see that I skipped the, it's so obvious that the x direction is 0 on this one that I skipped it. But so I just wrote down an AY and BY. So skipped a step there. But as we get more complicated, it's not, you're going to find we can't skip that step. But for this one, it's pretty straightforward. So here is my free body diagram. I've got an AY and a BY. What do? I look at this free body diagram to write my two equations. So I have to be true to that. So I'm taking moments about A. What is it? I got 7 times 5. I've got 4 times 3. I've got BY times 6. I've got 8 times 12. Now, are they positive or negative? This one, oops, I'll just show it. It's going to go counterclockwise, so it's negative. This one is counterclockwise, so it's negative. This one, counterclockwise, so it's negative. This one, clockwise, so it's positive. I then simply use algebra, true to my numbers, 8.17. Taking moments about B. 7 times 11. AY times 6. AY times 6. 4 times 3. 4 times 3. 8 times 6. 8 times 6. So like I say, everybody gets force times distance. Now, what are the... B is the center of my clock, so counterclockwise. So it's negative for that one. For this one, it's clockwise, so it's positive. For this one, it's clockwise, so it's positive. For this one, it's clockwise, so it's positive. I now have my equation, set it all equal to 0. It's got to all be equal to 0. I solve for AY. I get 2.83. So again, now in this case, both of them are positive, so it makes it a little bit easier. And I simply cross that out, and I put 8.17. I cross that out, I put 2.83. And that gives me my final free body diagram. And then we do our check. What do I see? What's going down? That's going down, that's going down. That's 15. That's going up, that's going up, that's going up. What does it end up to be? 15. So 15 up, 15 down. Okay, I'm going to pause there.